Yogaha Karmasu Kaushalam.
So, dear participants, we are starting a session called non-parametric test. In our earlier session, we discussed regarding the parametric test, where we discussed that when the data are interval or ratio, and when the assumptions of the parametric test, that is normality, that has been achieved, at that time we can go for a parametric test. But what should we do if the data are not normally distributed? Then we need to shift to the test called non-parametric test. So we may go for a non-parametric test under two situations. Situation number one is that the data scale is interval or ratio, but it is not normally distributed. So we are violating the assumption of normality. So we are switching from the parametric test to the non-parametric. So this is our condition number one, situation number one, that the data are interval or ratio but not normally distributed. So we may go for non-parametric. Second assumption or the second condition can be the data is itself ordinal in nature. The data is itself nominal in nature. Then what should we do? Then directly we may go for non-parametric test. So we may go for a non-parametric test if the data are ordinal in nature or nominal in nature. We can go for a non-parametric test. And for interval and ratio data, we can directly go for the non-parametric test if the data are not normally distributed. Now there are multiple types of non-parametric tests that are available. So let us start with one by one. The most popular non-parametric test, just I am sharing my screen. The most popular non-parametric test is chi-square. So let us start with the chi-square test. Chi-square test, first of all, when can we go for a chi-square test? What will be the null and alternative hypothesis? What are the fundamentals of chi-square test? What are the assumptions of the chi-square test? That we will discuss, and then subsequently we'll do with SPSS also. So chi-square test is what? Is a measure of relationship or an association developed by Carl Pearson in the year 1900. Carl Pearson, you all are aware, the same person who has given us the correlation coefficient. So the same person has also given the measure the strength or relationship or an association, and it is being given by the Carl Pearson. So chi-square test is a measure of a relationship or an association developed by Carl Pearson in the year 1900. It measures the association between categorical variable. Categorical variable, it may be a nominal, it may be ordinal data, or nominal to nominal, right? We have both nominal data, categorical data, or one is nominal, another is ordinal. So like this, but the purpose is to study the association. We would like to study the association between these two categorical variables. So we can go for the chi-square test of association. Now, technically what it is doing, it compares the observed frequencies with the expected frequencies. Chi-square test compares observed and expected frequencies. Observed frequencies means what? So observed frequencies means whatever we get in our data. After collecting the data, what we get is our observed frequency. Say for example, in a sample size of 100, we observed or we get the data regarding 60 respondents are male, for example, and 40 respondents are female. So observed frequencies are 60 and 40. Right? Whatever the frequencies we obtain, that is our observed frequency. Expected frequency are some ideal frequencies. Ideal frequencies means it is based on the assumption that the categories are equally distributed. It is under the assumption that the categories are equally distributed. So let us take the example that the same example, if the gender sample size is 100 and if we expect that the frequencies should be equally distributed, then the expected count must be 50-50, right, in a sample of 100. So whatever sample size, all our categories must be equally distributed. So this is what we mean by expected frequency. And it determines that whether these two variables are independent or they are not independent with each other. So chi-square test can be applied to both variables are measured on a nominal scale. This is situation number one. If both variables are nominal in nature, so nominal to nominal association can be studied with the chi-square test. Right? So if we have, say for example, gender, and if we have another variable called awareness regarding the uh, digital banking, say for example, and whether they are aware or not, yes or no. It is also a nominal scale variable. Gender is also a nominal scale variable. So we would like to study the association between two nominal scale variable, then we can go for a chi-square test. Similarly, we can also apply a chi-square test for interval and ratio data. For interval and ratio data, we can also apply chi-square. But we need to convert this interval or ratio data into some small number of categories or groups. For example, we have age that has been measured with respect to the continuous variable. We have asked that what is the age of the respondent, and respondent has given the age, say for example 71 year or 35 year, 21 year, 32 year, like this. The in terms of the years they are giving their ages. Once the ratio data like this is being collected, we need to convert this data into the groups if we would like to go for a chi-square test. So how do we convert them into group? So we can convert, say for example, 18 to 25, 26 to 35, 36 to 45, 46 to 55. Like this, there can be multiple ways in which we can convert the ratio or interval data into groups, right? And then we can go for a chi-square test. So any variable can be suitable for a chi-square test unless and until it is being converted into the categories. All variables needs to be converted into the categories, right? Even if it is interval or ratio, then also once it is being converted into the categories, it is suitable to run the chi-square test. It assumes that the observations are randomly sampled from the population. It is our assumption that the observations are randomly sampled. Randomness is everywhere in terms of parametric test. Also, we had these assumptions. Similarly, here also we are assuming that the observations are randomly sampled from the population. Now, the next one is the all observations are independent. What do we mean by that? An individual can appear only once in a table and there are no overlapping categories. So there are no overlapping categories and an individual can appear only once in the table. Right. So it means that all the data must be mutually exclusive. There should not be any overlap. And it also means that for a multiple purpose or multiple response analysis, the chi-square test is not appropriate, right? Because in multiple response, we do not have the entities which are mutually exclusive, right? There is an overlap. So For multiple response, we may go for a cross tabulation, but we should not go for a chi-square test. It doesn't make any assumptions about the shape of the distribution nor about the homogeneity of the variances. So it doesn't make any assumption regarding the shape of the distribution nor about the homogeneity of the variance. In terms of parametric test, we had these assumptions regarding the shape of the distribution and the assumption regarding the homogeneity of the variance. But here in terms of chi-square test, we do not have this assumption. What are the assumptions or limitations of chi-square test? So obviously the randomness assumption is applicable. So data is collected from a random sample. This is assumption number 1. Sufficiently large sample size is required. Now what do we mean by this? So because we are utilizing this test as an association between categorical variables. So within this category also, if the sample size is sufficiently large, then the small categories or the subcategories will also be represented with sufficient sample size. Right? If the overall sample size is very small, then it is possible that the subcategories will also have a very small sample size, and ultimately then it will not be take the conclusions from a very small sample. So it is assumed that a sufficiently large sample size is required. We need to apply chi-square test on the actual count data, not on the percentage. Always remember that we are applying the chi-square test to the actual data, count data, frequencies that we are applying. We are not applying this test on the percentage. And adequate swell size should be present, so it is very similar to the sample size assumption. So in each cell size also, subcategories also, we should be represent them as a sufficient sample size. Now there is assumption regarding the expected count, that this expected count should not be less than 5. When we calculate the expected counts, the ideal frequencies, these expected counts should not be less than 5. This is also one of the important assumptions. Observations must be independent, means each individual must come only once in the calculation, and then it should not be the repeatedly come. So all observations must be mutually exclusive. Then only we can go for a chi-square test. This is important. It doesn't prove causality. See, we are finding the association between two categorical variables. So association is something we can say a very loose word in terms of the relationship or association that we are trying to understand. That the when we found the association, what does it mean? It means that categories of one variable are associated with categories of other variables. Categories of one variable are associated with the categories of other variable. That is what we mean by association. But causality is something greater than the relationship or association. So causality means one variable is causing the another variable, which is not the case in terms of chi-square test. We cannot study the causality with chi-square test. So when we found some association, we cannot say that variable 1 is causing a variable another. We cannot say like this. So here we are not proving the causality. What is the hypothesis that we are testing? So null hypothesis is that the two variables are independent, and alternative is the two variables are associated. Right? Or in another words, we can say that there is no association between these two variables, and alternative hypothesis is there is an association between these two variables. we are applying the chi-square to the two variables, so it can be represented as a cross tabulation, and it is known as contingency table 2 by 2, contingency 2 by 2 table, where we have exposure, we have outcome, and it is just a nominal scale variable. We have yes, no kind of a thing, and we are trying to study the association. Now, it means that the categories of this exposure are whether they are associated with the categories of outcome or not, that we are studying. What is the equation that we will be applying for a chi-square test? So to calculate the chi-square test, we have this equation. This is a symbol of a chi-square is equal to sigma. F0 is our observed frequency and Fe are our expected frequency. So F0 minus Fe square divided by expected count, and this is our calculated value of chi-square. So if the difference between this observed and expected is small, it will turn out to be no significant difference. And if the difference between observed and expected is large, it will turn out as an significant difference. So that is what we are studying, the difference between observed and expected frequencies. Degree of freedom will be, in the case of a chi-square test, it will be R minus 1 into C minus 1. R minus 1 means row minus 1 and into column minus 1. So whatever number of row minus 1 and whatever number of column minus 1, the multiplication of this product will be our degree of freedom. Now we can understand this term by this our contingency table. I am going back. See, without the row and column of total, we may add one row of a total and one column for a total, but that will be excluded while we calculate the degree of freedom. So in this case, we have two row and two columns. So what will be our degree of freedom? 2 minus 1. So 1 multiplied by 2 minus 1. So 1. So 1 into 1. So 1. So our degree of freedom will be 1 in this case. So in this way, we can understand R minus 1 into C minus 1. Chi-square test is the study of association. It will tell us that whether these two variables are associated or not. Now let us suppose we found some association between these two categorical variables. Then the next question comes in our mind that whether the association is strong or weak, or what is the level of association. These two variables are associated with each other. So whether these variables are highly associated, moderately associated, what is the strength of association? So to measure the strength of association, we have this phi and Kramer's V available. See, directly when we go for a chi-square test, then we cannot compare the level of association, right? So for example, we have a chi-square calculated as 30.50, for example, and second chi-square calculated as 1000. So we cannot say that this calculated value of chi-square, which is a 1000, is more highly associated as compared to the chi-square which is having only 30. So we cannot say like this. Why? Because the calculated value of chi-square depends upon the sample size. Larger the sample size, larger the calculated value, smaller the sample size, smaller the calculated value. So we will not be able to comment anything based on the calculated value of chi-square. And that is why there are two coefficients available, phi and Kramer's V, that is nullifying the effect of the chi-square. So that is the reason we are dividing with the sample size there. We are nullifying the effect of the sample size. So that is why it is being divided with the sample size. So this Pearson chi-square provides information about the existence of relationship between two nominal variables, but not about the magnitude of the relationship. The phi coefficient is available to study the magnitude, and it is the measure of the strength of the association. So when can we go for a phi coefficient? So we have to always remember that when our contingency table is 2 by 2, then only we can go for a chi-square. When the contingency table is of 2 by 2, means 2 rows and 2 columns, at that time we can go for a chi-square test. So what should we do when our contingency table is greater than 2 by 2? Then we have Cramer's V. So Cramer's V, when the table is larger than 2 by 2, then we can go for a Cramer's V. So Cramer's V can be used. The purpose is same, to study the strength of the relationship between two variables. But when the table is 2 by 2, we may go for a phi coefficient, and when the table is greater than 2 by 2, we can go for a Cramer's V. And if Cramer's V is large, it means that there is a tendency for a particular categories of the first variable to be associated with the categories of the second variable. So you must have studied the correlation coefficient. You are aware regarding the concept of the correlation. Higher the value, it is indicating nearer to one value, it is indicating that there is a high degree of positive correlation. If it is related to -1, very nearer, then we can say that very high degree of negative correlation. Similarly, here also we are interpreting the values like for the phi and Cramer's V. If the values are nearer to 1, we can say that there is a very strong association between two variables. If the values are nearer to 0.5, we can say that the association is moderate. If the values are nearer to 0.30, 0.25, we can say that the association is weak. And nearer to 0, we can say that there is no association. So strength of association will be studied with phi and Cramer's V. Here in the equation, what is n and what is k? So obviously n is number of samples, number of cases, and k is smallest of the number of row or columns. What is k? Smallest of the number of rows or columns. Whichever is smaller, you need to put k is equal to that. This is an important discussion. Say for example, this data we have obtained and we are applying a chi-square test. What is the purpose? The purpose is which company's shipping services are better. What do you think? By looking at the data, will you go with company A or will you go with company B? We have these shipping services with company A and company B, and then the data regarding the damaged or okay, these data are given. Now we need to take a call that whether we'll go for company A or company B. So looking at the data, company A damage 15%, company B damage 33%. So similarly, company A is having 85% okay, company B is having 67%. So straightforward decision, company A is better as compared to company B, we will go with company A. Same data we are further bifurcating like this. Now think about the situation and then what will be your decision. The data is being further classified as heavy service and light service. With heavy service, we have the damage, for example, 67% are damaged with company A and 40% are damaged with company B. So for heavy services, damage is okay with company B, we will go with company B. Light services, 9% and 12% damage less, 9% will go with company A. Right? So we have for heavy services we'll go with company B, and for light services we'll go with company A. Earlier what was our decision? We'll go with company A. But now, as soon as we transferred our data into heavy and light services, our decision completely changed for heavy and light services. Right. So then what is the message? Message is that the result of the chi-square depends upon what? The result of the chi-square depends upon, it depends upon the way we categorize our data. The result of the chi-square always depends upon the way we categorize our data. Suppose we have categorized in only two categories, the result will be different. For a 5-point scale, the result will be different. For a 3-point scale, the result will be different. Right? So it is always you need to remember before concluding for a chi-square test that what kind of data you have collected and whether the further bifurcation if you are doing, then the result may be completely different. So here the problem area is what? Lurking variable. What is a lurking variable? Weight of the cartoon is lurking. As soon as we bifurcate the data based on the weight of the cartoon, the picture has changed. So before you act on the association, be sure to identify the effects of lurking variable. Always think that whether any lurking variable is present or not, and because of this present, if you still bifurcate the data, then the result will be different. So let us open SPSS and let us open the file. The name of the file is chi-square. Let me share my screen for SPSS. Chi-square. How many variables we are able to see? 3 variables. Scale, information sharing with supplier, and new product introduction. These are the 3 variables that we are observing. If we go into the variable view, scale values large scale and medium scale. 2 types of scale. Information sharing with supplier, we can see not important, least important, neutral, important, and very important. 5-point scale. New product introduction, if we can see not important to very important. 5-point scale. So what is our objective here? Our objective here to study the association between these variables. So one chi-square test can be applied to scale and information sharing with supplier. And second chi-square test you can still apply with scale and new product introduction. One by one you can do or simultaneously you can do. So for suppose if we are picking up 2 variables, scale and information sharing with supplier, what should be the null hypothesis? So null hypothesis can be there is no association between scale of the organization and importance given to information sharing with supplier. There is no significant difference in the scale of the organization and importance given to information sharing with supplier. This is the null hypothesis that we are going to test. How to test? So we can click on analyze, we can click on descriptive statistics, and we can click on cross. Then we have row and column available. So scale we can transfer as row, information sharing with supplier we can transfer as column. Simultaneously, if you wish to incorporate this variable, you can incorporate, right? And simultaneously it will provide you the results of the 2 chi-square test. But as we are learning here, so let us pick up only these 2 variables. Then in terms of statistics, we need to click on chi-square and we need to click on phi and Cramer's V and continue. In terms of cells, we need to click on expected count. Observe it is already there, so expected count. percentage, row percentage. We can click on continue, and then we can click on OK. Once we click OK, then the result is available in our output window. Let me share my output window. So this is our table number 1. It is known as cross tabulation. So cross tabulation, we have large scale, medium scale on as a row variables, and not important to very important as a column variable. Let us interpret the values. First of all, always your assumption regarding the expected count, it must not be less than 5. So if we see this one, here though we have this one, 0 cells, 0% have expected count less than 5. It must be 0. Certain authors are giving some freedom that if it is up to 30%, then also you can go with the chi-square. But beyond 30%, don't go for a chi-square. If you see this message as more than 30% of this have expected count less than 5, then don't go for a chi-square test. Right? You can go for up to cross tabulation, but don't go for a chi-square test. Now, let us interpret the results. So these counts are your observed frequency. This 11, 4, 5, 4, 9, these are the observed frequency. And then expected counts are given 5.2, 5.2. These are the expected count, ideal situations. How it is calculated in this case? It is calculated as row total multiplied with column total and divided by grad total. So for example, we are calculating for a cell which is having a large scale and not important. So this 11 is the frequency. Against that frequency, we are calculating the expected count, which is 5.2. So how 5.2 is being given by this software? So it is given as row total, which is 33 multiplied with column total. Column total means not important column. What is the total? 60. So 33 multiplied with 16 and divided by grand total. Grand total is 101. So 33 multiplied with 60 divided by 101. So your answer will definitely, it will be 5. And that is why it is being represented as 5. Like other, all these expected counts are calculated. Similarly, percentage also you can calculate. And these percentages are within the scale, means it is the row percentage. Right? It is the row percentage. Row percentage means if 11 is the count for not important, so as compared to 33, what is the percentage of 11? So it is 33.3%, like this. As compared to 33, what is the 4 is the percentage? 12.1, like this. So this is how the percentages are calculated. Now the second table, it is having a chi-square test, which is having a Pearson chi-square value is 20.21. It is the answer for this calculated value of chi-square, where you have this observed frequency minus expected one and square and divided by expected. So this is 20.21. This is the answer. And at 4 degree of freedom, the p-value is 0.000. Means null hypothesis can be rejected. And ultimately, what does it mean? If you are rejecting the null, it means there is an association between scale of the organization and importance given to information sharing with supplier. It means that this variable called information sharing with supplier is being given different kind of importance by large scale and medium scale organizations. They are not giving importance equally. Both organizations give different kind of importance. Say for example, if we count the total percentage of important and very important. So we have this 12.1 percentage for importance, and we have 27.3% for very important, right? So if we have 12.1 plus 27.3, so 39.4% is the percentage which is given by importance and very important total by the large scale, 39.4. Now, if we see for this medium scale, then 20.6 and 10.3, so 30.9%. Where in case of large scale, it is 39.4, but in terms of medium scale, it is only 30.9. So then, if the p value is less than 0.05, you can comment that large scale organizations are giving more importance to the information sharing with supplier as compared to small scale, as compared to medium scale organizations. Like this, further you need to interpret the values based on the percentages. So this is how we can interpret the results of the chi-square. Now, as the p-value is suggesting that you need to reject the null hypothesis, so there is an association. So the next question is, what is the strength of association? So the strength of association, we can see this symmetric measure, the phi and Kramer's V. So which one will be applicable? Will it be applicable phi coefficient or Kramer's V? So if you remember, phi means 2 by 2 and more than 2 by 2 Kramer's. So this is 2 by 5 matrix. So we'll go for Kramer's. So Kramer's V, the value is 0.447, though both values are same in this case. Kramer's V is 0.44, which shows a moderate association between scale and importance given to information sharing with supply. As the value is only 0.44, so we can say that there is a moderate association between these two variables. So this is how we can understand the chi-square test. Similarly, for the second variable, suppose if we want to include new product introduction, same result Pearson chi-square 0.009. So we are rejecting the null. So there is an association, but association is moderate, 0.339. Kramer's V, the value is 0.339. Association is moderate. And who gives more importance to new product introduction? So we have this 48.5 and plus we have 24.2. So we have 72.7%. That is being given importance, either important or very important. And 72.7 for a large scale. And for medium scale, only 13.2 plus 23.5, only 36.7. So straightforward, you can write that large scale organizations are giving more importance to a variable called new product introduction. But the association is moderate. So this is how we can understand the chi-square test. The second type of non-parametric test that we are discussing is known as sign test or Wilcoxon sign rank test. So let me share my screen for this test, sign test. We have two choices available for this test, sign test or Wilcoxon sign rank test. Now, do you remember our discussion on paired sample t-test, where we conducted the paired sample t-test for before after data, right? And we also carried out the normality test for before and after. At that time, we discussed that if the data were not normal, then what should we do? So if the data are not normal for the paired data, we need to shift to the non-parametric test and non-parametric tests. These tests are available called sign test, number one. Number two, Wilcoxon sign rank test. Both the choices are available with you if the data are before after paired data and not normally distributed. So you can go for, or alternatively, if your data scale is itself ordinal in nature like this, then also you may go for non-parametric test. So the scale of measurement here is ordinal. How do we consider that? How do you feel about your teeth? And this is a scale, 5-point scale. Wish I could change them. One, number two, don't like but can put up with them. Number three, no particular feelings one way or the other. Number four, I am satisfied with them. And number five, consider myself fortunate in this area. So you can see that there is a hierarchy. The numbers are increasing, and the feeling about the teeth is also increasing. But we cannot assume the equal distance property here. So from that, it is the ordinal in nature. The scale is ordinal in nature. So, but it is measured before and after, before the treatment and after the treatment. So it's a paired observations before and after the treatment regarding the certain number of children. So how this test works? So let us consider both the test one by one. First of all, let us take sign test. Sign test, it is used for the pair data as we discuss, because it is ordinal in nature, data are in ordinal in nature. It is very simple. Because suppose there is some improvement, we are giving a plus sign. If the values are decreasing, we'll give minus sign. Like this, it works on the sign of a plus and minus. So it is very simple and easy to interpret. And obviously, this is a non-parametric test, so it doesn't make any assumption regarding the normality or equality of variance like. But at the same time, it is not very powerful also. Non-parametric tests are our second choice. It is our second choice. First choice is always parametric test. But if the assumptions of parametric test we are not able to get, then we may shift to non-parametric. Here, why it is not powerful? Because we are losing the information. For example, you have data regarding the marks of the student. So this is a ratio data. Suppose you are ranking them first, second, third, fourth, like this, based on their performance. Then it becomes the ordinal data. Now, which one is better? Is it ordinal is better or marks in absolute form is better? Obviously, because if we have rank, we cannot get the marks. But if we have marks, we can convert it into rank. And we are assuming these 1, 2, 3, 4, the numbers. Though we are giving the ranking, but the distance is not equal, we are losing the information. So from that point of view, these non-parametric tests are not powerful. What hypothesis we are testing in sign test? So hypothesis is the sign test we are testing as the median difference is 0. The hypothesis is the median difference is 0. Median is what? It is dividing our data set into two equal parts. Right. So the difference between this median is the 0. That is what we are assuming. So what exactly it means? So if half of the differences are positive and half of the differences are negative, then our median will be 0. It means that suppose we have 10 participants, then 5 participants are feeling positive improvement and 5 participants are not feeling improvement. So it is deteriorating, minus sign. So if 5 is plus, 5 is minus, so then median would be 0. Right? And we'll consider that there is no significant difference. Any evidence which is more positive sign or more negative sign, that will be against your null hypothesis, but we require a p-value. So for example, we have 20 children like this, and we have the data regarding the before rating and after rating. So before treatment, what was the rating? How do they feel about their teeth? And once the treatment is given, again, how do they feel about their teeth? So it's a before and after data. How the software calculates the sign? So the change is measured. Change means after rating minus before rating. So 5 minus 1, it is 4 for the first child. For the second child, 4 minus 1, so 3. 1 minus 3, so minus 2, like. So here, a positive sign, what does it indicate? Positive sign is indicating in this case that after rating is higher than the before rating. A negative sign is indicating after rating is lower than the before rating. So plus sign indicates improvement, minus sign indicates deterioration. Right, so it uses the sign test to evaluate whether this data provides evidence that this treatment improves the children's image of their teeth or not. Right, and then the signs are given. So a change is positive, so we will give positive sign. So how many? 15 children felt better about their teeth. So we have given 15 positive signs. There is one negative sign, so one child felt worse. And there are 4 children felt the same, so 0 sign, right? So we have, if our null is true, then out of this 20 observation, we could have equally distributed plus and minus sign. Plus sign will also be 10, minus sign will also be 10. But if it is not equally distributed, then we have 15 positive signs. So it's a good evidence against your null hypothesis, right? You can reject your null hypothesis, but exactly we require a p-value that can be generated with the software. But it works on this philosophy of this sign, and in this way the signs are given. So then we require a p-value, and then p-value will be generated by the software, and it can give the exact value, and based on that we can decide that whether null is rejected or it cannot be rejected. The second non-parametric test for same purpose, before after, it is the Wilcoxon signed rank test. It is the Wilcoxon signed rank test. So is an another non-parametric test used for paired data. It uses the magnitudes of the differences, and it is more powerful than the sign test. Sign test only works on the sign. If you remember from, say for example, 1 to 5 or 1 to 2. So 1 to 5 is also a positive sign, 1 to 2 is also a positive sign, right? If the sign has improved from 1 to 2, then also a plus sign. If the differences or the values are increased from 1 to 5, then also a plus sign. So all things we are considering the same. So that is why it is less powerful, but here Wilcoxon test is more powerful than the sign test. How it is more powerful, we will discuss. For same example, let us consider before and after the data. Now we calculate the differences in the before and after. So what is the difference? So difference is, suppose 5 minus 1, so 4, 4 minus 1, so 3, like this. Now what it is doing, that the same observations 4, 4, 1, 1, like this. So it has been removed. We have 4 observations, or 4 children felt same. Earlier also it was the same thing. Now also after the treatment also they are feeling that it is the same thing. So difference we are considering 0, and 0 difference observations are not considered for the further analysis. So now out of this 20 we are removing those with this 0 difference, and now our sample is 16 only. So we have this 16. So we have removed number 5, number 10, number 11, and number 19. So now our sample size is 20, and this is the difference where we have 15 positive sign and 1 negative sign that we already know. Now we are considering this magnitude of the difference. So even a minus sign also we are considering the plus sign. And then we are arranging this data from the lower value to the higher value. First of all, we are removing the zero differences. Then we are giving the signs plus and minus. Then minus sign we are considering a plus one. And then we are arranging from the lower to the higher value. Then we are giving the average ranking. What we are giving? We are giving the average ranking. So the first one, it is obviously 1. Then how do we give this 3.5? Because we have 2, 2, 2, 2. So we are giving the average of this. So these are the tied observations. So second, third, fourth, and fifth. So 2 plus 3 plus 4 plus 5. This is the tide for this 2 to 5. So we are adding this number and dividing with total number of observations. These are 4. So 2 plus 3 plus 4 plus 5 divided by 4. So answer is 3.5. So we are giving 3.5 to all these our observations. Right. So up to 5 rank we have already given. Then we have starting with this again 3. How many 3? 1, 2, 3, 4, 5, 6, 7, and 8. Total 8 numbers. We have 3. So we have ended with number 5. So we need to start with 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 30 and divided by this number of observations. So the answer will be 9.5. So this is how we have given 9.5. And then similarly for this rank, the average rank is given 50. Like this average ranks are given. Then we need to calculate the total of the positive average ranks. So whatever the sign is positive, we are adding their average ranks and it comes as 132.5 and negative rank is 3.5. So if 132.5 positive plus negative rank, what would be the total? Total would be 136. And if the total is 136 and if we divide them equally, then 136 divided by 2. So what will be our answer? 68. So if the null hypothesis is true, then we could expect 68 for the positive difference and 68 for the negative difference. But what we get? We get 132.5 as a positive and only 3.5 as a negative. So it is definitely imbalance and more towards the positive side. But we require a p-value. So like this, the test is working and definitely null will be rejected for this kind of observations and it can be concluded that the difference is significant. Right? But we require a p-value to declare this. Let us open SPSS. Let me share the SPSS. The same data file we are working before and after reading, the same data file. Now let us apply this test. We need to click on analyze. We need to click on non-parametric test. We need to click on legacy dialog. And these are the related samples. So we need to shift to 2 related samples. Analyze non-parametric test, legacy dialogs, and 2 related samples. When we click on these 2 related samples, we'll get this. So variable 1 and variable 2, so we can convert before and after like this. And then type of test, we need to click sign test and Wilcoxon sign rank test. Sign test and Wilcoxon sign rank. These 2 tick marks we need to give. Just click OK. Let me share my output screen. to discuss the results. The first result let us interpret for sign. So as we were discussing this sign test, negative difference is 1, positive differences are 15, tie 4 and total are 20. And we didn't had p-value, so now software has given a p-value 0.001. 0.001 means you can reject your null hypothesis. So when you are rejecting the null hypothesis, it means that there is what is the null hypothesis? There is no significant difference in the feeling about the teeth before treatment and after treatment. Or statistically, the median difference is 0. That is the null hypothesis. So you are rejecting it, median difference is not 0. There is a significant difference in the feeling about the teeth before treatment and after treatment. And as the positive differences are more as compared to negative difference, so then finally you can conclude that the treatment is effective. Ultimately, what you can conclude that the treatment is effective. Now, Wilcoxon sign rank test. So same -1, positive 15, ties are 4, and then we were getting this the sum of rank 3.5 and 132.5, right? We discussed this average ranking. And as this 132.5, if we divide with this positive number 15, then we get 8.83. And this 3.50, if we divide with their respective sample size, then we'll get 3.51. And this is the p-value 0.001. So in this case also we reject the null hypothesis, and it can be concluded that the difference is significant. Same conclusion you can draw. And as the average mean rank for the positive rank is higher than the mean rank for the negative rank, 8.83 and 3.50. So 8.83 is higher. So then you can conclude that the treatment is effective. It has positive contributed. The treatment has positively contributed. So like this, you can go with this non-parametric test called Wilcoxon sign, rank test, and sign test. So it can be applied for ordinal data before after comparison, number 1. Number 2, scale data but not normally distributed data, then also you can apply this test. So this is how we can go with the second type of non-parametric test. This is sign test and Wilcoxon sign rank test. Now let us move ahead. The third non-parametric test that we are going to discuss is known as Mann-Whitney U-test. Mann-Whitney U-test. Now remember our discussion on independent sample t-test. Right? We discuss independent sample t-test. So independent sample t-test can be applied where we need to compare the two independent samples. We discuss regarding the gender and monthly mobile bill like this. So when you can go for Mann-Whitney U-test, suppose in the beginning of the test your data are not found normally distributed, then you can switch to non-parametric test, Mann-Whitney U-test. Number 2, if the data is itself ordinal in nature, your test variable, your dependent variable, right? Your test variable, earlier it was monthly mobile bill. So if this variable, test variable itself is ordinal in nature, then directly you may go for Mann-Whitney U-test. So this is how you can go with Mann-Whitney U-test. It is an alternative to the independent sample t-test. Assumptions of normality or equality of variance is not met. So we are not assuming any normality or equality of variances. Like many non-parametric tests, it uses the ranks of the data. Similarly, the way we discuss ranking in the Wilcoxon sign rank test, similarly, it also provides the ranking and then average rank, mean rank, all this. And since this test doesn't make any distribution assumption, it is not as powerful as the t-test, right? As compared to t-test, it is less powerful because we are ranking the data, so we are losing the information. So that is why it is not that much powerful as compared to t-test. Hypothesis, multiple ways you can formulate the hypothesis. It can be like that there is no significant median difference, or there is no significant mean rank difference in the whatever variable you are testing between your groups, suppose between gender, between say for example two cities or any two grouping variable, right? So your null hypothesis will be there is no significant difference in the in whatever your variable and then between the groups. So now let us apply this test with SPSS, Mann-Whitney U-test. Let me share the screen of SPSS one more time. This is the name of the file is sample data. There are so many variables. So how do we identify that for which variable this test can be applied? So we can identify like this. Say for example, these are the certain variables. It has been asked that give rating to the following criteria you consider important to choose the car. And these criteria are engine power, style, comfort, durability up to brand. So these are the criteria which are measured here as a least important, less important to very important. So 5-point rating, and we are considering this variable as ordinal in nature. We are considering this variable as ordinal in nature. But against this variable, against which variable we would like to go? So gender is available. Any two group variable is comfortable. So gender we can test. Then occupation we cannot go with because we have these 5 categories, right? Age also it is not has been categorized. So only gender is capable here. So between gender and each of these rating variable, we can go with Mann-Whitney U-test, starting with the engine power to brand. So now let us apply this test. You need to click on analyze, click on non-parametric, legacy dialogues, and two independent samples. You can click on two independent samples. As soon as we click all this rating scale variable, we can transfer here. Gender we can consider as a grouping variable, define group, and then whatever our coding, we have a 1 and 2 coding. So just we can keep 1 and 2. We can click on continue. Here the by default Mann-Whitney U it is available, and we can click on OK. Let us see the output. Where is the output? So one by one we can consider these are the so many hypotheses that we have tested. The first one is engine power. So what will be our null hypothesis for this rating with engine power? So it can be there is no significant difference in the rating of this engine power between male and female respondents. So this is our null hypothesis. Now 72 and 27, these are the sample size for male and female. Mean rank, if we observe, 49 average, 49.39 and 51.63. A slightly higher female average mean rank is being observed for the engine power as compared to male respondents. But whether is it significant or not? So we will get this p value from this table number 2, that is test statistics. And it is here 0.714. It is 0.714, last row. So we can conclude that there is no significant difference in the rating of this engine power between male and female respondents. As you can see that all these p values are less than greater than 0.05 only, right? 0.71, 74, 52, all these p values are greater than 0.05 only. So our conclusion for all these hypotheses will be that we fail to reject the null hypothesis. What will be conclusion? We fail to reject the null hypothesis. This is so ultimately both the gender give equal rating for all these variables, starting from engine power, style or comfort to the brand. Their perception, their rating, their importance with respect to the all these variables we can consider equally. There is no significant difference. So this is how we can go for a non-parametric test which is equivalent for independent sample t-test, that is the Mann-Whitney U-test. So participants, in this way we discuss some selected non-parametric tests. We started with the chi-square test. Then we discuss about the sign test. Then we also discuss the Wilcoxon sign test. And we discuss Mann-Whitney U-test. Chi-square test we discuss with respect to the association between two categorical variables. Right. So it is known as the chi-square test of the independence, that whether these two variables are related with each other or, and both the variables can be nominal to nominal or nominal to ordinal, or any variable, two variable that has been categorized, but you would like to see the association between two categorical variables, then you can go for chi-square test. So you may have in your primary data, suppose you are doing some questionnaire survey research, then you may have certain nominal variable demographics as a one variable you can pick up, and the second variable you can pick up that can be your any 5-point scale variable or any ordinal variable that you can pick up, and then you may run some association. Even if you have some nominal variable regarding, for example, some awareness you are measuring or yes no type of a variable, then also you may check the association between these two variables. Then we discuss about this paired data. So before after situations, always you may, for a non-parametric test, Wilcoxon sign rank test is more preferred as compared to sign test. So always you can go with the Wilcoxon sign rank test if the choice is the non-parametric test. And then we also discuss the Mann-Whitney U test, where it is the non-parametric equivalent test for the independent sample t-test. So any two group variable you can compare your ordinal scale data with any two group variables. Suppose the same survey data we had for the two, we collected from the two different cities, then yes, we can go or we can compare the two different cities data. Suppose the data has been collected from two different states, then also you can go with this Mann-Whitney U test, or any two naturally created two group you can compare with the Mann-Whitney U test. So this is how we can just anyhow we can just compare this Mann-Whitney U test. We can compare with the two group variable, right? So this is how we can go with the non-parametric test. Thank you.